Hi there, my name is Noah O'Connor, and today I'll be doing a presentation on college football analysis. So, what is my dataset about? The dataset basically covers all sorts of information regarding FBS college football teams and their performance through the years of data collection, which is 2013 through 2020. The data is sourced from the NCAA webpage and brings insight into each team's performance for each year through many different metrics and aspects of football, containing over 120,000 pieces of information in the dataset. The information covered in the dataset is quite extensive and covers things such as the number of games played by each team, as well as how many games of those were wins and losses, the offensive and defensive rankings for that team for that year, the touchdowns allowed for that team and their opponents, the special teams information such as kickoff returns, average yards per return, punt information for them and their opponents, such as where they fielded punts, red zone information, penalty yards through the year, including an average for each game and the total penalties committed, the total yards passing, rushing, as well as the number of touchdowns and the average for each play, the total first downs, first, second, third, and fourth down conversion percentages, pretty much any information you could want to know about a team. So, what can this data set be used for? The dataset has been used mainly to analyze the biggest predictors of success for college football teams. That's to say, what are the real determining factors that make teams successful? So we want to evaluate these determining factors towards a team's predicted success, alongside evaluating some common understandings, such as defense wins championships. This is a sentiment that is commonly echoed among college football fans, but is it actually true? So we want to look into that and data on both sides of the ball and see what we can find out about what best predicts a winning outcome for these teams. So actually getting into the data set now, looking at offense and defense and seeing how they perform seems to be a logical place to start. Because at the end of the day, if you can't score, you can't win. And likewise, if you can't stop the opponent, it doesn't matter how many points you score if every time they go down the field, they're converting the drive into points. So this is where we're going to start, and we'll do so by seeing if there's a correlation between rushing and passing offense and seeing if one has more of an impact than the other on the outcome of the game. So in the left diagram, you can see a scatter plot for offensive yards per play in comparison to offensive touchdowns. So ideally, the best teams would be in the upper right corner with the most yards per play and then converting those plays into touchdowns. If we look a little closer into this data, though, in the diagram on the bottom right, we can see the split between passing and rushing to see what the most successful teams have done. So in this graph, the bubbles that are larger represent higher offensive rankings, and then the x-axis represents passing percentage and the y-axis represents rushing percentage. So what you find is the most successful teams typically towards the middle, but they have a little bit lower passing percentage, anywhere between 35 and 45%, and they have a 55 to 65% rushing percentage for their plays. The first model used to determine offensive success correlating to winning percentage was a linear regression. The data that was chosen to be used for the model was pass attempts, pass completions, interceptions thrown, passing yards per attempt, rushing yards, rushing attempts, and fumbles. These were chosen since they give a holistic view of how the offense is doing both positively but also negatively. So if they're fumbling a lot and not creating yardage, passing or rushing, then it's also a good indicator of the offense. Before using the data, though, it needed to be standardized since the data in the data set encompasses many different scales and values. So, for example, some of the data in the data set refers to yardage, others may relate to percentages, and others just refer to the total number of plays or fumbles. So, to bring this to a common scale, center scaling was performed. And essentially, what that is you calculate the average for each piece of data, for fumbles, for instance, and then whatever value you have, you then subtract it from the average that you calculated. So you kind of get a scale of where it is in comparison to the average, no matter what the type of data is. And then you take this number and then you divide it by the standard deviation that was calculated for that data set also. And this allows all the data types to be brought down to a common scale without changing the meaning of the values in and of themselves. So after we done this, we divided 30% of the data set to be used for training the linear regression to predict the winning percentage, and then the rest was used for testing the data. The result of the linear regression was a calculated mean squared error of 0.02297. This is a fairly accurate representation of the winning percentage. Looking closer, though, at the metrics that we used to train the linear regression, there's some interesting things that you can find out. So, pass attempts, as it increases, actually has a more negative effect on win percentage. This is maybe because if you're passing more often, that means you might be in worse field position where running isn't an option. So, for instance, if you constantly find yourself in fourth down and long, you can't really realistically run the ball. It was also found that rushing increases winning percentage, but only slightly. And this kind of lines up with what we saw, where more rushing attempts are usually done in better offensively ranked teams. But the most interesting thing we found was that pass completions have a major impact on the winning percentage. And this kind of makes sense. If you have a low pass completion and you just run the ball, the defense can kind of pin their ears back and work to contain the offense around the line of scrimmage. And you kind of become one dimensional in that sense. The offensive stats were also run through lasso regression to see if better results could be had by using a different model. The lasso model is based off of a linear regression, but implements a cost function that penalizes the use of many parameters by penalizing large errors much more than small ones. This helps to stop overfitting and lowers the mean square error while also helping to find the best predictors for a better result. Also implements an alpha value. The higher that the alpha is, the less columns from the dataset or features are used in the prediction. And then the closer the alpha is to 0, the more columns or features are used. So you have to strike a balance in choosing the alpha so that it minimizes error and gives good results, while not being too little information for the model. The model doesn't give much performance benefit over linear regression in this case. It was hypothesized that this happened because the initial linear regression features removed highly correlated predictors like rushing attempts, rushing yards, and rushing yards per attempt, since they kind of paint the same picture and are more or less redundant. Therefore, the ones that were chosen happen to be very good predictors already, and the lasso regression couldn't make many improvements since the linear regression was chosen with good features to begin with. As you can see in the diagram here, the mean square error increases over a certain value of alpha. So in this case, it was actually tested with many alpha values to determine the best version of the lasso model. But none of them really gave a performance benefit, as mentioned before. To further test if any more optimizations could be done, it was also tested with a random forest regressor model, which ended up giving the smallest mean square error value. Essentially, what the random forest regressor model is it uses many decision trees on parts of the training set, which is done with the replacement in this case. And depending on a threshold value, a decision tree may choose different branches and it feeds into other decision trees. As each decision tree is trained and becomes more accurate, then all the decision trees are joined together to give an overall more accurate prediction model. When this is done with the training data and then tested with the test data, the result for the mean square error ended up being 0.02083, which is the lowest of the two other models we've discussed. Now that we have seen the best predictors of winning percentage on offense, let's kind of do the same thing and take a look at defense. So good defenses obviously don't allow touchdowns and typically have low yards per play allowed, but this isn't always the case. In some cases, there's teams that let the other teams drive down the field, but they end up being really resistant in the red zone and end up forcing points typically by field goals. You can kind of see this reflected in the diagram below, where teams on the right are really low on the graph for touchdowns allowed, but they allow almost 10 yards per attempt. So the columns from the data set that were used for the defensive model are yards per attempt, yards allowed rushing, average sacks per game, tackles for loss per game, as well as fumbles recovered and opponents intercepted. These were chosen because, again, they paint a very good picture of if you allow low yards per game, you're getting to the quarterback and sacking them, hitting people behind the line of scrimmage, recovering fumbles, and then intercepting the ball, you're doing a good job on defense, since it seems likely that those correlate to a higher winning percentage. Or a lower winning percentage if you're not doing well in those regards. So after standardizing the data and doing the training and test split, as we've mentioned before, the linear regression model resulted in a mean square error of 0.0236. And then as you can see in the diagram here, you can see that the biggest predictor is actually the amount of interceptions that the defense was able to get. This ended up having the largest impact towards winning percentage in a positive sense. Something interesting you'll see as well is that sacks also had a major impact towards the winning percentage, but in a negative sense. Um, I think this is likely a misinterpretation of where the data relating to sacks in the data set wasn't for the defense, but instead sacks on their quarterback on offense. So this makes sense why this is kind of inverted to what we would expect. Also interesting to see was that uh, yards allowed rushing and yards per attempt, while they did have a negative effect, they were roughly equal to that of interception on the game, but in a negative sense. Um, so they didn't scale like you would expect. Um, so it almost seems like as long as the defense, even if they're letting a lot of big plays, as mentioned, you can still have a pretty good defense that doesn't allow touchdowns. And that kind of reflects what we saw in the diagram before. After running the defensive stats through the lasso regression, it gave roughly the same performance even when testing with different alpha values, giving a mean square error value of around 0.023. And opposite of what we saw with the offense, when doing the random forest regressor, it actually gave a mean square error of 0.0252. While this is still pretty good, it actually performs worse than the linear regression and lasso regression, which is opposite to what we saw last time. This is likely because after looking into the data, the yards per attempt had many outliers in the data set, and it probably couldn't get a clear-cut prediction for the wide range of values since how it handles the thresholds and passing it to the other trees in the prediction model. In conclusion, this dataset provided many interesting conclusions to be determined. Offensively, it was determined that the single biggest predictor for winning percentage is pass completions, and it wasn't really even that close. But rushing yards also had a substantial impact. Defensively, you could conclude that the interceptions are the single most impactful play defense can make to flip the momentum in a game, um, with tackles for loss and fumble recoveries also being important. Um, Having more of an impact on the game than holding the opponent to a strictly low yardage game. That being said, pass completions were far more important to the outcome of the winning percentage than interceptions and overall defensive play. So it seems that the old adage that defense wins championships doesn't have as much merit as you may expect. This kind of makes sense if you think about it for a second. Some of the closest games between the best teams are often determined by who has the ball last and can put themselves in positions to score. Looking back at the data set and considering some improvements or considerations that could be made, um, I think it could be interesting if information about the percentage of games played at home and the winning percentage for those teams at home, if those could be added to the data set, I think that would be pretty interesting to see how the crowd and game attendance was a factor in those games. I also wanted to note that data from 2020 may not be the most valid. Different conferences use different COVID protocols. The original football schedules weren't necessarily followed, so FSU couldn't play UF, for example, because they're in different conferences. And teams also start in different parts of the year, and those that were impacted by COVID more heavily didn't even get to play the same number of games, so it's kind of a skewed data set for 2020. I also do think it'd be interesting, though, to add to the data set how injuries affect the winning percentage of games. Obviously, having a quarterback injured can have a major impact, but what about other skill positions such as running backs and receivers or the defensive line and defensive backs? Also, something like college game day, where there's a huge event on the campus for one of the teams. Does that have a correlation between the home team winning and taking those games away? Or is it just a fun, entertaining way to get people to attend the game? But that has been my data set. Thank you guys for coming to my presentation. If you have any questions, I'll be more than happy to try to answer them. Thank you.